Welcome, everybody, to the third talk at this morning session. The speaker is Sven Bachmann from the University of British Columbia, and he will speak about the quantum Hall effect, time reversal invariance, and the FKM index.
Thank you very much. Thanks to, is this loud enough? Yes? I can put it louder if, okay. Thanks to all the organizers. It's really a pleasure to be here and seeing all of these young and enthusiastic faces. So I've been tasked to tell you about a lot of things. So we'll see how far we get, but let's get started. So I split my 3 lectures into three topics. I hope to go a little bit faster on the 2 initial topics and have more time for the last one. We'll see. But today I will start with some words on the quantum Hall effect. So this is a huge topic, whether in physics literature or in the math literature. So I will just say a teeny tiny little bit about it. One other thing is, whenever you look up quantum Hall effect, everybody has their favorite setting. So there's many different settings in which you can describe the quantum Hall effect, different from a physical point of view, different from a mathematical point of view. And I've picked one, right? So you will see if you Google things, there's lots of different settings. They're all equivalent whenever they can be compared. It doesn't mean that they're all equivalent at all, okay? All right. So let's do a little bit of physics. So the physics of the quantum Hall effect, and again here I actually pick a particular version of it, is we think that we have electrons moving in a large disk. In fact, later on in the course, this disk will be the infinite plane. But for simplicity, let's start with a finite disk. And I have here a magnetic flux. So you can think that there's really a coil. And through that coil, you can pass an electrical current that generates what physicists call a flux, which pierces this disk here. And so now, if you remember, maybe you had a bit of physics, the Maxwell's equations. If you have a time-dependent magnetic field or a time-dependent magnetic flux, that generates an electric field, or an electromotive force, is usually called. Now, okay, if you go to the Maxwell's equation, you see that if you have a flux like this, which changes with time, there's an electric force or an electric field that goes, around that changing flux. So let me call it E. Okay, so if you have electrons now in this 2-dimensional plane, they feel this force of this electric field that would like them to go around in circles. Okay. So that's the sort of setting you have. Now, there's one more thing that I have to say in the quantum Hall effect. These electrons are in the plane, but there's something important. The plane on top of this has a magnetic field, constant magnetic field. So let me just put B's everywhere. So this whole thing is in a constant field that is perpendicular to the plane. Okay, so there's 2 different parts of magnetic fields here. There's a constant one throughout the plane, and there's this time-dependent one piercing the plane at one point. Okay? So that's the setting. Now again, if you go back to basics of electrodynamics, you know that if you have a charged particle moving in a magnetic field, there's what's called the Lorentz force. The Lorentz force is perpendicular to the velocity and to the field. These electrons are trying to move along here. There's this perpendicular B field here. The right-hand rule, you see that these electrons, depending on the charge, will actually not flow in circles around, but flow also like this. There's also a component like this. This is what's called the Hall current. So this is called the Hall current. Okay? So you see, it's a current. You're trying to drive the system, right? Trying to move these electrons in circles. It turns out, because of the presence of the B field, these electrons do not go in circles, but go radially. Okay? And this is sometimes called an off-diagonal conductance. And that's the Hall effect. That's classical. So it's very old. Hall is not the Hall that got a Physics Nobel Prize and whose name is engraved in some stones up here. It's an old Hall of the 19th century. I think he was a student of Maxwell. And his original paper, he computed this and said, this must be a mistake. This cannot possibly happen. So this is a classical thing, right? So the presence of this is well known in classical electrodynamics. Now, I wrote quantum Hall effect. So what is quantum about the quantum Hall effect? Quantum Hall effect is, now you know, if you, again, go back to your basic physics. In basic physics, you know that there's a relationship between the voltage and the current, right? The voltage and the current are related by resistance or conductance if you put it on the other side of the equation. So here, you know, I will replace voltage and current by electric field and current. And I will define what is called the Hall. So this is the Hall conductance, sigma Hall. And this is the ratio of the Hall current by the electric field, which would also be the time derivative of that the magnetic flux. So okay, so far so good, right? What is quantum about it is that if the B field is large enough, you will see that in fact this doesn't take an arbitrary value, but it takes an integer value in the right units. Okay, so the quantum part is this, that this observable, the conductance, the electrical conductance, is quantized. Okay, and so that was measured in the 80s by von Klitzing and his collaborators. And it's an experimental curve which has absolute, so he plots the Hall conductance as a function of the B field here. He has very strong B fields. And you see a curve, and you see that this curve has extremely well-defined flat parts. And these flat parts correspond exactly to integers. Okay, so this, I think, originally was an experimental observation which called for, you know, theoretical and mathematical explanations. Also, precisely, it's an experimental fact, which is, however, extremely perfect. So it's not, you know, your typical experimental result where people tell you, look, there's a flat part, and in the, you know, the graph does something like this. It's perfectly flat, which calls for really, you know, mathematicians like that sort of thing. It's perfect, right? So how do you explain the appearance of this integer? Okay, so that thing, where should I continue? Maybe I'll continue. So the explanations, the original explanations, of course, you know, this is physics, so this came within a year of the publication of the experimental results. The first one was by Thouless and collaborators. There's various papers. The one which is very cited goes by K and N because there were four authors. And he managed to explain that by really understanding what is happening in terms of the topology of vector bundles. Okay. Now, of course, if you understand that in terms of topology, it's kind of natural. You know, topological quantities are kind of by construction independent on local changes somehow, right? The genus is the genus. You can deform your torus as much as you want as long as there's a hole. There's just one hole. The genus is exactly one. Okay, and so this was the insight of Thouless. I will not go into that because although this was the first explanation of the quantization of the quantum Hall conductance, it is the one that does not really generalize very well to interacting electrons, and that's what I want to do. The other one, so you know, the measurement is 1980. I think that's 1982 or something. At the same time, Laughlin, he explained that a little bit differently. Physicists use the word gauge invariance. And I will say a little bit more about that. It's related in mathematics to an index theory for Fredholm operators, so I will explain a little bit that. And that is turns out that Laughlin that is the part that will generalize to interacting electrons. So these explanations are made if you assume that the electrons here feel these magnetic fields, of course, but they do not interact with each other. Okay, so these are non-interacting electrons. Of course, they interact with the environment, but not with each other. Okay, and so that's what I want to explain a little bit. Maybe now this is really a little too loud. Okay, so in order to have something a little bit concrete in mind, although it will not play much of a role, I will start by writing a Hamiltonian that describes this situation. Okay, so precisely it's free fermions, so it's a very simple Hamiltonian. So if m is the mass of the particles, the electrons, you have the momentum minus E over c, and A, so E is the charge of the electron, c is the speed of light, p is the momentum. Oh, I forgot a square, of course. Yep. So I have to think of that as an operator acting on L2 of, so I will do that in the plane, so of R2, or of course, you have to slightly change that a little bit, so I put that in parentheses. You could also do that on the lattice. Eventually, I will actually go to the lattice. But for kind of initial explanations, it's easier to think of the continuum here. Okay? So that's the Hamiltonian. And what is A? So I will just erase this now. Or maybe I'll keep the picture, actually. Why not? So A is called the magnetic potential. A generally determines the magnetic fields here. So you want to have that you pick A to be, so 1/2. So B, is just per vertical x. So if you take that, is so B here, the vector is B E3, right? And if you take that, the curl of A is exactly that little constant vector B. It's a little calculation. There's other choices of A, by the way, but if you take that concrete A, you will generate this B. So far, I haven't put this the flux in there. Okay. Okay. Really, I'm not particularly interested in the Hamiltonian itself, but there is a Hamiltonian that describes this system, and it's a Hamiltonian, as you see, for one particle. It's a one-electron Hamiltonian, right? And it's sufficient because these electrons do not interact with each other, so I can describe everything by looking at just one electron. All right. Now, this Hamiltonian is, with that particular magnetic field, can be... you have to do your workout here. My God. So you can actually you can diagonalize it explicitly. Okay, it's a little bit of a calculation, but this sigma is not a good idea. So I'm just going to write spectrum of that Hamiltonian. Right? It's an explicit calculation. It's once you know how to do it, you can do it, and you see that it is again up to numerical constant. The spectrum are just all integers. Okay, where the C maybe I should be a little bit. C depends in particular on the B field. Okay, so you see it's a very particular spectrum which is full of spectral gaps, right? There's C and then 2C and then 3C. So it's a Hamiltonian with lots of spectral gaps in there. Okay. Good. Good. I did not ask you to do this calculation for the homework exercises. I don't know. It's not particularly interesting, I think. So all of these things, they're called. So the spectral subspaces, they're actually infinitely degenerate. They're called Landau levels. Now, I'm telling you all of this because if you ever open a book or open a page talking about the Hall effect, you will see these words, so I'm telling you what these are. So Landau level is the spectral subspace associated to these eigenvalues. Okay? Good. Now, finally, I'm coming to what I actually want to say. I have a Hamiltonian, and I want states. Because at the end of the day, all of these topological effects are related to states. So I will come to to Daniel's states in a second, but for now, a state is something slightly different. So here I will think, these experiments were done at very low temperature, and everything can be well understood at 0 temperature. So well, let's look at what is a 0 temperature state. Okay. A 0 temperature state is just a spectral projection of that Hamiltonian. Okay? And not any spectral projection. You pick, so pick a mu, let's say positive. Okay? And write p mu. I don't know if you like this sort of notation, but it's the spectral projection of the Hamiltonian. Let's just write it like this. Okay, so that's a projection on the spectral subspaces up to value mu. Okay, so this would be 0, below the first value of C, and then it jumps to a non-trivial projection onto all eigenstates corresponding for the eigenvalue corresponding to n equals 1, and so on and so forth. Okay? So let's not discuss that. That's what physics tells you. A 0 temperature state is given by the spectral projection on all states up to a particular value. That value mu is called the Fermi level. And that projection is called the Fermi projection. Good. So now that I have a state, I can maybe try to relate that state to this, oh my goodness, to the whole conductance. Good. Pardon me? Chi is a Heaviside function with a jump at 0. Yes. Okay. So I'm almost there. The last thing, you see, in this whole setup, I've told you about everything except for the phi here, right? So phi the B is just that constant B field. So you need to add this flux. Add this flux. So what is the flux again? If you remember some physics, otherwise here's a definition. So a flux through a flux is a flux through a surface. So you pick a little surface, and the flux through that surface is the integral on that surface. So let me call that surface C of A. So you integrate that magnetic vector potential. Okay, that's called the flux. So what I want, I want to pick an A such that this is a certain constant for every little surface here, and 0 is as soon as I'm outside. So a particular choice that I can make is I take A to be the gradient of the argument function. Again, the normalization here is a little irrelevant. Argument of the vector x. Or let me write z. So I can think of the plane as a complex plane. It turns out that this is the natural thing to do. And then you have a natural argument function, okay? And so if you take that, so I will call that, it's again a chi. This is bad. I wanted to call that chi, so let me call that epsilon, whatever. Okay, so that function, the argument function, I just call it epsilon. Yes?
Sorry, one question. Are you
yes.
going to fix mu? Or
so this will be for every mu. So mu or phi? Mu. So for what, the results will depend on the choice of mu.
So it's your choice.
But it's my choice, yes. So you can think of fixing mu as fixing the density of your system, for example. That's one way to think about picking mu, yes. Right, so that function is called mu. And you see, of course, the argument function is a bit messy, right? Yes? Yes, so there is an A, So there is an A here, and there's an A flux. Let me call it F flux. You see, there's two magnetic components in my physical system. One is the constant B field that permeates the whole plane. And then there's the thing that it's this little flux, okay? So that I write here is just for the little flux. Okay. This one is the rest. All right, so that function is not a good function. It's not single valued, but however, its exponential will be single valued. And it turns out that if you define u to be e to the I, so it's not chi, it's epsilon, right? That's a good unit as a multiplication operator on my L2 space. Yes, exactly. I fix mu. For the rest, I will not even write mu anymore. So mu is fixed. And for things to be non-trivial, it will be above the value c here. Otherwise, everything is trivial. But think of mu as being fixed, and in fact, I will forget it. Okay. So that as a multiplication operator on my L2 space. Right. And once you have that, there's a little theorem due to Avron, Seiler, and Simon. I think it's 85, so it's not really so much later. You know, mathematical physics is not always decades after physics. In that case, it's just a few years, so it's the same time. That said, OK, look, I can actually prove that the Hall conductance is related to all of these quantities up to 2 pi. So I can compute that as an index, and I will tell you what an index, I still write the mu here. U, pu, u. OK, so that's a non-trivial result. That's a non-trivial theorem that you can compute that. And I have to tell you what this index is. So you see P and U. So P is a projection. It's a projection operator. U, P, U star is also a projection operator. So this is an index of a pair of projections. Where? Oh my. So the index of PQ, so I just write this for 2 general projections, is dimension kernel P minus Q minus 1 minus dimension kernel P minus Q plus 1. OK? So it's a definition. Now, one thing which you see immediately from that, it's a dimension of a space, right? Dimensions are integer valued. OK? So once you manage to prove this, then automatically you've proved quantization. OK? So that's really so you have to. You can understand this, and I think that's actually how it is also written in the paper, that this is a version of the argument of Laughlin. So I said at the beginning, in physics, there are 2 arguments. The one of Thouless, which is really related to vector bundles. And this one is the one related to Laughlin, which has to do with gauge invariance or gauge transformations, which is this U here. OK, good. So that maybe I'll get to your question. That's it.
Very short question.
Yes.
That is probably also an index in the Fredholm.
Yes. So this one you could also write it as the Fredholm index. And now to be sure, I think it's U. It's P. It's the Fredholm index of. Is it PUP or UPU? I think it's P. Yeah, exactly. So that is so this exactly is equal to that, if you like Fredholm indices. And it's a good point, right? So depending on what you like and what you know, you will express all of these things in different fashions. The fact that you can express this as a Fredholm index brings you the idea that Fredholm indices, so this is an index which is invariant under deformations of that. And being invariant under deformation, that's exactly what you're looking for, right? So this is an integer, and of course, kind of naturally, if you deform things, this integer will remain an integer, but you can actually make that in terms of a homotopy theory if you relate it to a Fredholm index. All right, good. So what do I want to say? When did I start?
Half an hour ago.
Okay.
Actually,
25 minutes, yes, okay. Because I've noticed that my predecessors were very good at stopping on time, so I'll try to do the same. Okay, so I will just say the following thing. Just note two properties here. One is that the index of PQ is index of PR plus index of RQ. So in a sense, if you think, what are we physically talking about here? So, this is a fact that you can prove from that. Pretty obvious fact, actually, if you think 5 seconds about it. But also physically, it says, well, this conductance is about charge transport. I'm transporting charge. And this will say, well, if I, let's say, increase this flux and move some charges around, I increase it a little bit, I move some charge around, and then I increase it again, I move again some more charge, well, the total charge transport better be additive, okay? So this mathematical property of the index is a very natural physical property that you would expect for any such index, okay? It's this sort of things, I think this is beautiful mathematical physics because precisely these mathematical properties of somewhat abstract objects totally correspond to the physical intuition. So that's one thing. And then having that, and in fact, so if U is compact, so compact as a multiplication operator on L2. So if you don't know what a compact operator means, it doesn't matter, but you can think of that as U is acting only locally around the flux insertion point, but is not acting out there at infinity. Think of that. So if I make a local perturbation of my system only, then what? Then in fact this index of P, UP, U star will actually be 0. So you see, it tells you that the charge, if I just touch my system too locally, then in fact there's going to be no charge transport at all. The whole conductance will be 0. Okay? And if you combine the two here, you see, if you have a U, which gives you a certain whole conductance, and then you perturb that U a little bit by another U of that type, of a compact type, then the value of the whole conductance will remain constant. And that, again, is an instance or an example of what exactly you're looking for, namely that local perturbations do not change the value of these topological indices. Okay, so out of that, you can these two things together, sigma whole is a Now, this word is loaded with meaning in mathematics, right? The topological invariant in mathematics is loaded with meaning. It's typically associated with invariance under homeomorphisms, okay? So in this whole business of topological states of matter, it's not the same, right? So in fact, in the approach of Thouless, it happens to be the same. But really, here, and in the rest of this talk, and I think for the rest of the week, whenever you see that sort of mention of a topological invariant, it just means that things are independent of local deformations or local changes, okay? So that's, this notion of topological invariant and topological phases is a bit dangerous because for mathematicians this means something, and what it means for physicists working on this is not the same. Okay, although they're related, but it's not really the same. Yes.
When U is compact, what does it correspond
So you see, if you think of so here you could look how this A decays at infinity. And it decays like 1 over r square in 2 dimensions. That's just not sufficient decay. To make it compact, you would have to have a fast decay away from the insertion point. Okay, again, it's this idea that it's U is acting very locally, namely kind of with an exponential tail, or not. You can also think that's not the A I've taken, but you could take another one. You know, the argument, if you want, increases linearly as you go around. You could also, in fact, compress all that increase along one line and say that A is fixed, is constant everywhere, but just has a jump of 2 pi here. You could also do that, and then you would see that along that line, I will come back to that picture, you can go all the way to infinity. That jump is there all the way to infinity. Okay. Yeah?
My question, I'm guessing that U is not unitary?
No, it is unitary. U is that is a perfectly well-defined unitary. It's not compact. Pardon me? Unitary operators can be compact. So compact here, for those who don't maybe know, compact means you can approximate it by finite rank, so by a finite matrix. Right? I'm here in an infinite dimensional Hilbert space. So in general, an operator there, even a bounded operator, is not just a matrix, but a compact operator are exactly those that I can obtain as limit as finite dimensional matrices. Okay? So, you know, if you write this in some sort of position basis for physicists, right, that's exactly what it means. You know, if you look at the matrix elements of that in the position basis very far out at infinity, it will have to be essentially 0, so that you can approximate that by truncating that matrix. Okay? Yes. Oh, sorry.
So compact Hilbert space must be finite dimensional.
So, wait. So, sorry. Yes, exactly. Very good. Thank you. That's what I forgot. Yes. So, yes. Thank you. The corresponding, the thing in the exponent. Yes. Thank you for the comment. That was a mistake. All right. Good. All right. So, you know, from that, if you are a mathematician and you look at that, you might, you know, maybe in particular here in Boulder, you might like K-theory of C-star algebras. And so obviously people saw this and then took it over. And there's a whole branch of understanding quantum Hall effect and its variants using K-theory of C-star algebras, because what K-theory is, it's about thinking of differences of projections, essentially, okay? So you can go and everything is very clear and perfectly well-defined if you use K-theory. But I will not do this here. One of the reasons is, and this is what I wanted to, you know, so maybe I'll do that at the end. I still have a little bit of time. So, you know, there is an explanation of all of this in terms of this projection and this unitary. Okay. Now, here is, you know, in my title, there's also something called time reversal. So let's add that extra ingredient to this to my system. So what is the time reversal on a Hilbert space? Well, it's a definition. It's an anti-unitary. So it's an anti-linear operator, right? That leaves the inner product invariant. So it's an anti-unitary T, such that, and here I have electrons, and it's important, T square has, so T is a unitary operator that squares to -1. Okay, so that is something which is particular to fermions, if you know what that means. Okay, that the square of the unitary is -1. So if you want an example, you might wonder, how do I do this? So in fact, on the Hilbert space I gave you before, you cannot have that. But you can have that, for example, on L2 of R2 C2, if you want, now it's a spinful electron with a spin 1/2, hence the C2 here. You can take T to be complex conjugation. That's complex conjugation with respect to L2 if you want, time a little matrix -1, 1, 0. That matrix here squares to -1. Okay? That's complex conjugation. So, this makes it antilinear. This makes it square to -1. Okay? So that's just an example, but you can keep that in mind. There are such things, right? Such as, so they're called fermionic time reversal operators or odd time reversal, depending on where you look. So in what I'm going to say, by the way, this morning we had these spin systems. Okay, so I will have to work in a slightly different. For me, it's important that these are not spins, but fermions. And I will explain what, also briefly later on, what the corresponding algebras are. Some modification of the structures you've seen this morning. Okay. So here's a little proposition if you want. So I gave you before a Hamiltonian, okay? But you could have different Hamiltonians describing the whole effect. But suppose that you have a Hamiltonian which commutes. So you have such a fermionic time reversal operator. And you suppose that my Hamiltonian is time reversal invariant. Okay? Let me then. So that's, maybe I should write. That's time reversal invariance. In fact, let me write it. You see, that means that if you do the time evolution and then reverse time, you get that it's e to the I t h t, right? H is invariant, but t is antilinear, so it will change the -I into an I. All right? Anyway, so if you have that, then the whole conductance is actually 0. Okay? So I will actually spend a little bit of time proving this. But you see, before I go ahead, what does this mean? So before we have this beautiful topological state called, that describes the Hall effect, you have in fact a family of states. They correspond to possibly different values of the whole conductance, and this is perfectly well classified by this index and so on. Now, what this proposition is telling you is, well, if you have time reversal invariance of my system, then in fact all of this is completely trivial. The whole effect, the whole conductance is 0. Okay? Now, if you're a physicist, you're like, why do you even say this? Because if you're a physicist, you know that the magnetic field changes direction when you change time. So, there was a magnetic field. If this is supposed to be time reversal invariant, well, that magnetic field be better 0. And because it's the presence of this magnetic field that causes the whole current, then obviously the whole conductance has to be 0. Okay? So that's why. But let's quickly see this. Let's, it's a bit of an example of how to use these definitions here. So you first check. I gave you a U before, right? So you can check that TU is U star T. T is a multiplication operator by a phase. It's e to the I, a real number. Okay? And so if you take T through it, it will give you a U star. And then, then it's a calculation. Index of P, U, P, U star. By the way, here I actually don't even need this is not really needed actually here. Okay? Sorry. This is not what I want. So the whole conductance will be given by, the U, P, U star. Again, mu is fixed, right? And now I want to, so if you look at this, you see if I add on both P and Q are unitary. What do? I change the basis really, but it's the same object. So the index is invariant under rotating both projections by a unitary. So I can just as well write index TP T star, TU P U star T star. Okay, just a change of basis in a sense. Okay, but now let's look. So here, what is that? So TU, this is U star T. Okay, and what do we have? So TU is U star T. And then I would like to, so actually let me write the whole thing. It's probably easier. So it's U star T, P. I can do the same thing here. I get T star U, right? Now you see, what do I have here? I have a spectral projection of that Hamiltonian upon which I act with time reversal. But the Hamiltonian, right, commutes with T. Hence, its spectral projections also commute with T. Okay? And so this happens to be P. That's by assumption. Okay? Maybe it's a little too low for those people sitting in the front row. Okay? Okay, so what do I get? I see that this is equal to index of TP T star, U star. This is not what I want to have. U, right. So now that I've done that, I can remove this for the same argument. So I just get P in the first guy, right? And with the second, what do I get? I get U star PU. So far, there's no minus, right? So far, pardon me? So here I have a U star, right? Here I had a U. Here, right? So there's no minus. Now I can use unitary invariance again to get index of U P U star P. It's the same unitary invariance of the object. And now you can look up there the definition. If you exchange P and Q, you change the sign. So that is equal to minus index of P U P U star. Okay, that's by this definition. Okay, so you see, if that is the whole conductance, it's equal to minus itself. So it has to be 0. Okay, so it's a silly little calculation. Does that, now here's the, this is perfect. I will be able to essentially finish with that little calculation. I'll still leave that up there for now. In fact, here I just use that T is unitary. TT star is 1. That's all I use here. I will use T squared is minus 1 later on, not here. So maybe it is confusing that I introduced it here. Okay, so all right, so with all of this, you can ask, so now so here's the question now. Is everything topologically trivial? Again, topologically in the sense of physics, so to say. Triviality in the presence of time reversal. Okay, I mean the whole conductance is 0. It's supposed to be a trivial state. The answer, of course, is no. In fact, there's still, before all of these whole states, they were characterized by one number, the integer, which happens to have a physical meaning, the whole conductance. Okay, so there's an infinite family of states labeled by an integer. So in the presence of time reversal, we still have a In fact, there's still, again, another topological index called the Fu-Kane-Mele index. But this one is just Z2 valued. So now, if you impose time reversal on your system, then in fact the whole conductance is 0, but there's still two distinct families of states. And my purpose for the rest will be to describe that. Okay? I want to describe what this Z2 value index is, but I'll do it in an interacting setting. So, here's another. So this was question 1, and we will answer that question. Now, question 2. In both cases, right? So what did this whole lecture? I started with a Hamiltonian for 1 electron, and I said, well, I describe as many electrons as I want because anyway they don't see each other, so they're non-interacting. And if you look, I define the whole conductance in terms of P, the spectral projection. It's a spectral projection of a Hamiltonian for 1 electron. Okay? So the question 2 is, what can I even write if I have interactions? Right? This whole structure completely collapses. If I have interactions, I don't have this 1 particle Hamiltonian. I don't have this 1 particle state, which is given by a projection, right? All I have left is what Daniel explained to us this morning. There's some algebras and some states, but not at all. It doesn't look like it's close to this. There's no natural generalization of that sort of approach. And in fact, for any of the other approaches, it's the same to interacting systems. So what to do with interacting systems? In particular, there is no Fermi projection anymore. Okay? And so although, for example, K-theory is beautiful, I know it explains all of this perfectly right. Homotopy theory of Fredholm operators is beautiful. It explains everything you want. But all of this completely collapses if you say, well, in fact, my electrons are interacting even very weakly just because the fundamental objects are just not there anymore. Okay? And so luckily, we will also be able to answer that question. Okay? This is a more recent result. So what I've said that was essentially understood in the 80s. And what I will talk about in the last 2 lectures is rather in the last decade or so, a bit more. Okay, will I stop here? I think that's all I wanted to say for now.
Are there questions? Yeah.
All right, so I got 2 questions. So
Yes.
First, all of this sigma h and everything depends on this parameter mu you
Yes.
chose. Can you explain to me what mu means physically?
Yes. So you see, so I told you this the spectrum. Here's the spectrum of H, right? And it's just on the line. So let's say here is 0. There is a constant. Let's forget that constant is 1. So the spectrum is just 1, 2, 3, 4. Okay, and so on. And the mu, if you think it's a spectral projection, right? So you have to think that the physical state is like this. So if I pick mu to be 2.5, right? It's here. So what will I do? That spectral projection will be the projection onto all states corresponding to that degenerate eigenstate and that degenerate eigenstate. So that means I filled, I really take my physical system and put all of these particles that correspond to these 2, in fact, infinite dimensional projections into my system, into that plane. And as I move mu, I fill this one first, then I fill this one first, and then so on and so forth. And it turns out that everything I told you about can be done provided mu is in a spectral gap. So it's exactly between 2 integers. What happens at the integer, that's a totally different question. But what we were looking at is when mu is in the spectral gap. And so these projections are just very simple and correspond to how you filled your physical system. So that's why I said it corresponds also to the density. If you think in an infinite volume, there's an infinite number of states, but somehow you can still change the density by changing mu. And mu then will correspond to changing the Hall conductance. In fact, this integer is the number of these energy levels which are filled.
I guess the way I would ask this question, because how do you change the state to change mu, I guess, is what I'm asking.
You mean physically now, or?
Yeah, like what does it mean physically? I guess I see what it means mathematically, but I cannot
Well,
make sense of what we're actually changing. Fair enough.
I'm not sure. I'm not enough of a physicist to be able to. Maybe other people in the audience are better.
Uniform magnetic field. You keep everything else fixed, and you change the magnitude of the uniform magnetic field. But
I see.
It's really changing the density, but the important quantity is the density of electrons kind of per unit of magnetic flux in the system. So the easiest way to control that is usually with magnetic field.
In fact, I think the original experiment showing quantization is the plot I was talking about is in terms of the magnetic field.
I see. And I guess the second question is you brought up the topological invariance or triviality. I'm a mathematician. Can you explain to me what it means for physicists?
So yes, I've tried, and I think it will hopefully become a bit clearer with during the rest of the week. Okay, but so had I explained to you. No, maybe let's start with what I explained to you. There's this index of a pair of projections, okay? So one thing you can see is that if I change my u such that u minus 1 is compact, the index it remains invariant. And you can think that it's not just one u, but it's a family of u's. So you can think of that as being some sort of deformation of your system. And you have a quantity which stays constant under deformation. So that's kind of close to, now, there's other approaches to this where this becomes much more like a topology as you think of it, where really it's about homotopy theory. And that I will actually try to say a bit more about next time.
All right, I'll ask more next time then.
Yes. You will probably still not be happy, but because this is in a sense still a bit of open question.
Further questions? Okay.
So usually disorder is very important for the Quantum Hall effect. Can you see that entering in this formalism?
Oh, absolutely. So I purposefully put that in a dusty corner, right? So of course I wrote all sorts of propositions, but unlike my predecessors, I was very unprecise. My theorems and proposition come with assumptions, okay? And so for example, so concretely here, there is this theorem of Avron-Seiler-Simon that come with assumptions on the spectral, in fact, on the matrix elements of the spectral projection. These assumptions are satisfied if mu is in a spectral gap, or if you have strong enough disorder in your system. Okay, so yes, and in fact, if you want to understand all of the quantum Hall effect, not only the aspect I talked about here, you need disorder. That's perfectly well understood in the non-interacting setting. In that case, absolutely not understood mathematically in the interacting setting.
You had said that there's two different approaches in the beginning, Thouless
Yes.
and the next one. And but when you said that this index is really the index of some Fredholm operator, I mean,
Yes.
that is on a vector bundle, no? Or like, and there's a base space.
Yes, so the easy way to think about the other approach is actually to take a translation invariant system, so where you don't drive your system with a magnetic flux, but with an electric field. And then really what you have is P, you can fiber P in momentum, so you get a family P of K. Let's say you're on the lattice, so K lives on a torus, and you're in two-dimensional lattice, right? So and so now P of K is a finite dimensional projection for each K. You know, in the simplest setting, a one-dimensional projection, so that gives you a line bundle of the torus, okay? And associated to the line bundle, there's an actual proper topological invariant, which is called the Chern number, or the first Chern class. That's a number, and that number happens to be an integer, which is the Hall conductance. Again, that requires some proofs. But in that setting, that is really a bona fide topological invariant. But since this is exactly the thing that does not generalize to interacting systems, that's why I didn't describe that. you shout enough.
So there's the index defined by Fredholm, and there's the Chern number index, and one is analytical, the other is topologist, the topological.
Yes.
And I've heard this anecdote saying, oh, there's some correspondence.
Sure. So again,
has this community been exploring that
yes.
correspondence?
Yes, absolutely. So this correspondence for the Hall effect is very well understood. It took a while actually to understand how, although if you go through physics, obviously they're the same because it's the same Hall conductance, but to relate that index, which is, as you said, analytical, to the index of a line bundle, which is topological, you can do that. You can show that the Chern number equals this index. This is work of, I mentioned Avron, Seiler, Simon, so it's them, Graf, Eisenman. I mean, there is a series of papers starting in the 80s and until the 90s, which show exactly when and how these two things are equal.
And is this done through just borrowing some big index theorem, or the details are laid out?
Yes, so again, it depends a little bit which paper you read. Some are very abstract, others, but they all, I mean, the one I have in mind uses actually some ideas of non-commutative geometry, but you can state a big theorem of non-commutative geometry or do it by hand. And they tend to be done by hand because they were done by mathematical physicists who don't necessarily like big abstract theorems, but you'll find everything in the literature.
Thank you.
There was one question down here.
Regarding the previous disorder question,
yes.
I wonder if we can think of this way. So in your story, you assume that you fix mu,
yep.
and you assume that mu can continuously change. But if it's a clean system, if it's perfectly clean system, the mu cannot continuously change. It can only be in those levels. It's only because if there's disorder, you can continuously change.
Absolutely, yeah. That's from a physical point of view, absolutely correct. If you want to be able to continuously change mu, and in your system you need disorder, and you need these gaps will be filled with localized states, and that can be dealt with. Precisely the fact that these states are localized. You see here, if you have a spectral gap, by essentially abstract nonsense, you know that the matrix element of the spectral projection are, so it's a consequence of Fourier theory really, are decaying fast. P of xy decays fast in the distance x and y. If you have localized states here, it's the same. Being localized essentially means the same thing, that P of xy will be decaying fast. And so both things work perfectly fine, and if you want to describe physical systems, then you need this disorder. But it's an added complication which I didn't want to introduce here.
Okay, thank you very much. Thanks the speaker again.